These are the answers to Module 6, Problems for Students, Part 1. There's really just one problem here with 4 parts. We're going to take each of the 4 parts here. Let's read through the problem. We've got a solubility product constant for strontium sulfate and a solubility product constant for strontium fluoride. They're 2 different values. And the first 2 parts of the problem ask us for the molar solubility of strontium sulfate and strontium fluoride in water at 25 degrees C. The third part asks us to, it says an aqueous solution of strontium nitrate is added slowly to a liter of a well-stirred solution containing 0.020 mole fluoride and 0.10 mole sulfate. You may assume that the added strontium nitrate solution does not affect the total volume of the system. Which salt precipitates first, and what's the concentration of strontium ion in the solution when that first precipitate begins to form? And then part D, as more strontium nitrate is added to the mixture in part C, a second precipitate begins to form. At that stage, what percent of the anion of the first precipitate remains in solution? Okay, this problem for sure looks intimidating, but we're just going to break it down and do one step at a time. So we're going to start with part A. It's all about writing the solubility equilibrium and understanding what's happening. So at 25 degrees C, the solubility product constant KSP for strontium sulfate is 7.6 times 10 to the minus 7th, just a repeat of the problem statement. So the first thing we're going to do is we're going to write and balance our solubility reaction. So we write strontium sulfate solid dissolves to form strontium ion and sulfate ion. You can see, because of the double-headed arrow, that this is an equilibrium reaction. It does not go to completion. We don't really know how far it goes, but it doesn't go to completion. If it did, that would be a single-headed arrow pointed to the right. So since we don't know how much dissolves, we're going to call that unknown X. You can call it whatever you'd like. This is really in terms of molarity. So at the equilibrium, whenever we reach that point, the concentration of strontium ion is equal to the concentration of sulfate ion, and we're going to call those concentrations, or that single concentration, X. Call it whatever you'd like. Okay, remember when we do equilibrium problems, we ignore the concentration of undissolved solids and of pure liquids. So when we write our expression, what we get is KSP, which is 7.6 times 10 to the minus 7th, is equal to the concentration of each of the products raised to their stoichiometric coefficients divided by each of the reactants raised to their stoichiometric coefficients. But in this case, strontium and sulfate are both X, so I have X raised to the first times X raised to the first, or X squared. And we ignore undissolved solids, so I have nothing in the denominator. So I just have X squared is equal to 7.6 times 10 to the minus 7th. And I get 8.7 times 10 to the minus 4th moles per liter. And we're finished. That's the solubility of strontium sulfate at 25 degrees C. Pretty easy, actually. All right, let's do the second part. The second part. Actually, we're going to do what's called an icebox or a rice table, because this is going to set us up for success in subsequent problems. The problem methodology is not different. The way I organize my data is a little bit different. Okay, so if I take the first letter in each of the words reaction, initial concentration, change in concentration, and equilibrium concentration, I get rice. So this is why it's called a rice table. Sometimes we just leave off the reaction part, we write it, but we don't really include that in the box. We just draw a box around the concentration, the numbers themselves, and so that's called an ice box. However you want to do it, doesn't matter, you get the same answer. All right, so again, this is pretty straightforward. We don't have any strontium sulfate. We have 0 strontium ion and sulfate ion at the beginning of the problem. When we change, we have X amount dissolved, and my equilibrium is just the sum of the first two lines. 0 plus X is X, right? So I write my equilibrium expression. I get X squared is equal to the KSP, and I get my same answer, 8.7 times 10 to the minus 4. It's just going to be it'll be easier to see what's happening when the problems get more complicated, and they will. Okay, part B. We're going to do the same problem, only with strontium fluoride. We write our reaction, and we notice now the only thing that's really different is now one of the products has a stoichiometric coefficient of 2. So we set up our Rice table. Again, we ignore the undissolved solid. We have a 0 concentration initially. Our change is now X for strontium ion, but because of stoichiometry, it's 2X for the fluoride ion. So my equilibrium concentrations are now X and 2X, and we write our equilibrium expression. We get the KSP, which is 7.9 times 10 to the minus 10th. That's equal to X times the quantity 2X raised to the second power because we raised it to the stoichiometric coefficient. So we have 4x cubed. Divide both sides by 4, take the cube root, and I get 5.82 times 10 to the minus 4th. Little bit more interesting, not difficult. Okay, that's our answer to part B. Now let's go to look at part C. We have an aqueous solution of strontium nitrate that's added slowly to a liter of a well-stirred solution containing 0.02 mole fluoride and 0.1 mole sulfate. The question is, which salt precipitates first, and what are the numbers involved in that? So when the strontium ion is added, we're either going to get strontium fluoride or strontium sulfate. So let's figure out how much strontium is required in each of these scenarios. They have different KSPs, so we'll get a different number. Okay, so now we do this, we pick one to start with, so let's pick the fluoride, doesn't matter which one we start with. We have our KSP, is the concentration of the strontium ion times the concentration of the fluoride ion squared. Now the unknown we have is strontium. We know the KSP, it's given. We know the fluoride because it's in the problem statement. 0.020 moles in a liter of well-stirred solution. That's 0.02 molar. I plug that in for my fluoride. Now I solve for strontium. And I get about 2 times 10 to the minus 6 molar. Okay, we're going to do the same thing for the sulfate. We know the sulfate concentration. It's 0.1 mole divided by 1 liter, so 0.1 molar. We plug that in. Again, we solve for strontium. We get 7.6 times 10 to the minus 6. Okay, straightforward. Since 2e minus 6 is less than 7.6 e minus 6, the fluoride salt of strontium has to precipitate first. We get to that level before we get to the 2.0 times 10 to the minus 6 before we get to the 7.6 times 10 to the minus 6. We're starting at 0. Admittedly, these are low concentrations, but which one will I get to first if I'm coming from 0? I get to 2.0 times 10 to the minus 6 first. So that's associated with strontium fluoride, so that must precipitate first. And when it does, our strontium concentration is 2.6 times 10 to the minus 6 molar. And that's our answer to part C. Now let's do part D. Part D says as more strontium nitrate is added, a second precipitate begins to form. Well, we know what's going to form, right? It's going to be the sulfate. But at that stage, what percent of the anion of the first precipitate remains in solution? All right, so as we just said, the second precipitate to form is strontium sulfate, and we know that will appear when the strontium ion is 7.6 times 10 to the minus 6. We just got that number in part C, right? So when the strontium ion concentration is 7.6 times 10 to the minus 6, now we can calculate F, and we can compare that number to what we had originally. So let's plug that in. We know KSP is going to be 7.9 times 10 to the minus 10th. And that's going to be a function of the strontium concentration and the fluoride concentration. Now we are solving for the thing we don't know, which is the fluoride concentration. You can see it's squared. So we can divide both sides by 7.6 times 10 to the minus 6. We take the square root, and we get 0.0102 molar. That's the fluoride concentration when it starts to precipitate. Okay, initially we started with a 0.02 molar from the beginning of part D. Now we're down to 0.0102 molar. So what's remaining? Well, 0.0102 divided by 0.02. So 51% of the fluoride is what's remaining. Okay? A complicated problem, lots of moving parts in this problem, but straightforward because we just keep on writing our equilibrium expressions, figuring out what we know, what we don't know, and plugging those things in and solving for the unknowns. Pretty straightforward. That's the answers to the extra problems part 1. There will be more videos for part 2, which will consist of additional problems.